Le Chatelier's principle states that it...
Okay, we can shut this down. Is that going to work? This is very old. You can't even download the player anymore because of the chance that all these files contain viruses is so high. On the other hand, I think that's IT's problem. I finally found the player on an old drive I had. Okay. This is the reaction FECN aqueous 2 plus goes to Fe plus 3, aqueous plus SCN. It has a pale color, that one's dark red, and the other one is clear. We can see all the pieces dancing around with that. If we added SCN, what would happen? Which way would it shift?
Towards the product.
So if we add NaSCN towards the product, so what color should we go? Lighter or darker? Lighter. Let's add some. See what happens. It got darker. So adding SCN shifted it which way? The reactants. Why? This is on the product side. Whatever you do, nature tries to undo. We greatly increased that. So it had to shift left in order to reduce the amount, and then the other one went back up. We can do a change in temperature. How do we do that? Oh, different reaction. We did this we actually did this in like actual class. So as a review, this is a, well, this is an interesting puzzle. They didn't put the energy term on here. Let me see what, no. Hopefully they don't tell you, because what I'm gonna increase or decrease the temperature. We'll see which way it goes, and then you should be able to tell me if it's endo or exothermic. So we apply the flame. We then set, okay, which way? It takes a long time. Oh, they added the heat term. So that wasn't going to be as clever as I thought. We increase the heat, shifts to the right, it gets darker. We actually did this one in real life though. Let's do change in pressure because that's what we're doing now. Iodine exists in both a monoiodide form and a regular I2 form in the gaseous state. The I form that isn't a paired molecule is clear, while I2 is deep, rich purple. If we increase the pressure, which way should it shift? To reactants? And then what should the color become? Darker. See, that's the case. Shows increasing pressure. The number of molecules should shift in the little blocks. I think it takes so long because there's a guy explaining. I just shut off the sound because I didn't want to hear him anymore. And we can see the number of molecules have decreased of the clear form, and then we have more of the darker one moving around. The overall number of molecules is now less because of the increase in pressure. And of course, if you decrease pressure, you pull the piston back, you should get the opposite occurring, where it goes to the side with the most molecules to try and make up for that. Can't believe I got that working again. What else do I got? Whoa. Review, way back when. A2 plus B2 goes to 2AB. See the molecules come together, makes the activated complex, and then goes down the other side. You can now shift all of these. Do I need to scroll? No. So we can increase the bond strength of some of these. Increasing the bond strength. Come on. Can I just grab it? No, I can't just grab it. Do we want this exo or endothermic? Endothermic. So let's make. Let's make it a really high hill. And no. And then we can increase their kinetic energy. See what happens. It goes fast. Let's make it. There's not that much energy in the environment. Ooh. So this one you can actually see the activated complex being formed. Let's decrease it even more. What happened there?
It went back to reactants.
Went back to reactants. If you don't have enough energy to get over the activated complex, it doesn't work out. So nice. Okay, back to what we were doing. Graph the change of concentration. I think we left on this. Did you actually draw this? This is example 2. Graph the change of concentration if the volume is decreased. Okay. But we did the previous one where it was increased, did we not? Oh, hold it.
We skipped it.
Oh, right. I said I was going to come back to it. Yeah. That the volume is decreased. And then I blew up the balloon. So what happens to the pressure if you decrease the volume?
You decrease the volume, the pressure
Yeah.
increases.
And for which, hold it. You can't see what I'm talking about because it's on my other screen. And I've been talking to myself. There we go. I asked you if you're on this one example too. You didn't even see what I was looking for. Let's move that over here a little bit. Go there. What happens to concentration to all of them if you increase the pressure by decreasing the volume?
Concentration increases.
Yeah, so they should all spike up. So you should get that happening with all of them. And since the pressure is going to be, the volume change is going to be the same for all of them, it should be proportional. They should be the same. And now they're going to react. So the concentration has increased for all of them. Which way is it going to shift? What would reduce that concentration?
What was the question?
If we've increased the concentration of the entire system, which way could it shift to reduce the concentration of the system?
Could it go both ways?
Why to the products?
Because there's less molecules.
Less molecules. And this is our example that I was doing the other day, where we were shifting back and forth stars to this, because you just overall get less molecules. If you take away 3 stars, hello, I have to leave, and then they go away, you get back 2, the whole system's decreased by 1. Oop, went the wrong way. And so it's going to shift to the products. What will that look like on here? So, if it's shifting to the right, what will NO do? What will its curve look like? It's 1. Samuel, do you have the notes?
No.
Andrew, do you have the notes? Put away the laptop. What is laptop?
No, I was looking at it on there.
Looking at what on there?
That's just something.
If you need an extra copy, they're over on the side.
Yo, I have it.
Okay. So it's shifting this way. That should go down. What should NOCL do?
Go up.
Go up by what proportion?
This same.
The same as NO or less than NO?
The same thing.
The same. Both the numbers are the same. So they're both 2 to 2. So whatever this is, this should go up by about the same amount. I'm going to use a different color because I'd rather think I put myself in a spot where those are going to end up being really close to each other. And then what is CL going to do?
Go
Down.
down by half.
By half. So I think that's about half. So if this is X, that amount is X, then this amount is 1/2 X.
Mr. Newell,
Yep.
I just need an explanation on the graph. I don't really.
So which way are we shifting? Is that part okay?
You said you were shifting to the product.
Yeah. Do you know why though?
No, because I thought in PLOD, we had it so that if there's more molecules on the product side, or on the reactant side, then it should shift to reactant. There's 3 in the reactant,
Yeah.
2 in the product, and in PLOD, we have the arrow pointing the other way. And now it's pointing up.
Why would we have the arrow pointing the other way?
Because there's more molecules.
Oh, you're talking about entropy, right?
What are we talking about? I don't get the arrow.
Entropy is when we look at entropy and enthalpy, and if they opposed each other, you get an equilibrium. This is already at equilibrium.
How did you know that it was in the equilibrium?
Because I just gave it to you as like, this is at equilibrium. And you're right, this side is more entropic. This side has the heat turn, so it should be added. But now that it is at equilibrium, if we decrease the volume and increase the pressure, which way is the equilibrium going to shift?
Decrease the volume and increase the what?
Pressure.
Then we go to the lesser side.
To the lesser side. Because if we increase the number of particles, so go back to my crazy example. Go away. Pull all that away. No, those can stay there. If we decrease this volume, make it all squishy, there's now less room for them to bounce around in. And the concentration's actually gone up. There's more particles per square foot or meter or whatever you want to measure. And so if it gets rid of 3 stars, oops. 1, 2, 3, don't go back. It will shift over here and you get 2 happy faces. But the overall number of particles is decreased by 1. And so the concentration is now, and you can keep doing that, and now the concentration has kept back down. So when you increase the concentration, it'll shift to the side with the less particles to try and offset that increase. Okay. In Le Chatelier's term, whatever you do, nature tries to undo. It is undoing this increase in pressure by decreasing the pressure. If we decrease the number of molecules, the pressure is going to go down.
And then for the ground, how does that?
So shifting to the right, what happens to the amount of NOCL?
It increases.
It increases. So from here, you see the increase.
But what's the difference between that? I kind of forgot what the difference between the spike up and then going down is compared to just it going like.
Oh, what the first thing we did, volume is decreased. So when you decrease the volume, which gas did we decrease the volume of?
I thought it was in all of them.
Yeah, it is of all of them.
So,
I phrase it that way because sometimes people go, oh, well, did you decrease the volume on the parabolic side or the reactant side? And it's like, oh, it's all one balloon. You can't pick sides. It's on all of them. So all of them spike,
okay.
Oh,
right?
And all of the spike increase.
Because we increase the pressure. I'll get you right up.
Okay, because as the volume decreases, pressure increases.
Yeah.
So that's why all of them spike up.
That's all of them spike up.
They all spike up, but they all go up.
Yeah, they all go up, and it's a spike, yeah, they all spike up. And then you see the change to equilibrium. So this starts to go up because they're shifting this side, and these both go down, and they do so in a proportion of 2, 1, 2. Because they're going to this side does so via stoichiometry. 2 particles of this react with 1 particle of that, so the 2 to 1 disappear and make 2 particles of this. So this should go up twice that Cl2 goes down. And the amount they go up and down should be equal for NO and NOCl.
Oh, and you're gonna graph the forward kind of reverse rate, or?
We could. I didn't ask for it on this, but did we? But what will happen to the rate if we increase the concentration of everything? Increase. Which rate will increase? Forward or reverse? If the concentration's increased on both sides. Both will increase. And it shifts to the right because this side, this rate increases the most. So if I was to do a quick reaction rate graph, so time, rate, forward, reverse, and purple being blue plus red. So there we have the rate, decrease the volume. They both spike up. But the forward rate spikes up more. There's more molecules, so it is more affected by concentration. And so that rate, this is the actual reason why it shifts. Now the forward rate is much faster. Now as soon as it starts leaving, what happens to that forward rate? Pardon? It slows down because the particles are shifting. And as they shift, there's less of them. So that then you get that classic sort of look that looks like this, and the rates equal out. And once they are equal, I'm going to make it purple again so we can show that they're overlapping.
Sorry, could you just go down to where it says, or is there CL?
Yeah, CL. So it's in a 2-2-1 ratio or a 1-1 and 1/2 ratio, whatever you want to write that. Okay?
Yeah.
Andrew? We're going to immediately do another example.
We'll try to find.
Katie?
So if you decrease volume and increase pressure, does that decrease or increase the concentration?
If for gases, pressure is the same as concentration. High pressure is high concentration.
Okay.
Because when you think high pressure just means there's a lot of molecules in that volume. That's what concentration is.
So it'll shift to the lesser side, but is that in terms of like entropy or enthalpy?
It is not in terms of entropy or enthalpy. Entropy and enthalpy got us the reaction. So in terms of the reaction, entropy favors this side, enthalpy favors this side, minimum enthalpy, maximum entropy. And so it is an equilibrium. Now that we're decreasing the pressure, we don't have to worry about that. What we're worrying about is which one has the highest rates.
And
So how
Yeah,
do you
wouldn't this
know
be increasing
which one is the lesser side?
Yeah.
Oh, you just,
Decreasing-
how many particles?
decreasing pressure.
3 particles?
Oh, bro.
2 particles.
Because
Isn't that
increasing the
entropy?
pressure increases concentration.
You do the same thing in entropy, but we're not talking about entropy.
So it's just about the particles.
It's just about the particles, yeah. Yeah, it's not about entropy at this point.
So then the faster
So
reaction,
that's
then
what
the
it,
reactants
that's what
will
it
be.
is.
Sorry?
So then it would be faster on the reactants.
Yes, it would be fast. There's more particles, so it's more affected by changes in concentration. Yeah?
So does that green arrow indicate which way the reaction is going to go towards afterwards?
What's it going to do after equilibrium?
Reaction shift towards.
Reactant shifted this way, and then what happens at equilibrium?
They're equal.
They're equal. So now there's no more shifting. Back to
and then wait. So now they're just stay in equilibrium. Is
yeah,
that
it just
happens?
stays. So when we shifted it, it shifted over, and then it just stays there in a new equilibrium.
So then why did it go towards the products in the first place? Is that just like how it goes always?
That's just how it goes always. Yeah. We did the rate one already. When we decreased the volume, increased the pressure, that made the forward rate faster. It's a new system now. And so it shifted to the right, but eventually that forward rate dropped until it met the reverse rate, and they now have a new, faster but equal rate, and more of the product is on the right hand side. Remember when I had the tubes of the brown NO2 gas? This is not this reaction. Put it in hot water, it got really brown.
Yeah.
But if you left it in the hot water, it would stay that brown. It's at a new equilibrium on a different side. That was due to temperature, not pressure. But it would stay there. If we went like this, then it will shift to the right. And if, let's say this was green and that side was red, then it would just become greener and it would stay that. There's things you can use for that, where they change how opaque they are at different pressures. You can use that to measure pressure in a system as a little gauge. There was a hand I think here somewhere. Yeah.
So does any equilibrium always go back to equilibrium? Or does, like, what kind of adjustments do you have for it not to?
Oh, anything, if it's if you make a change to equilibrium, it will go back to equilibrium. For a change to occur, the equilibrium would have to be overwhelmed in such a way that, for example, taking a closed system and making it an open system. So if you keep siphoning off NOCl, it'll just keep shifting right. You added so much of one thing that, like, the amount of Cl2 just increased by orders of magnitudes. We're not adding 10 moles anymore, but like 10 to the 3 moles. It'll just all go the other way, and it will become overwhelmed. Temperatures are so high that the reaction just goes to one side. Yeah. Technically, though, it will always be a tiny bit at equilibrium if it's a closed system. We already did this. Towards products. Pressure is increased, volume is decreased. If pressure is increased, the volume is decreased, the reaction will shift aside with the what number of molecules? More? Less? Less number of molecules. Andrew? Another question on this one, or are you working on something slightly different?
Slightly different, but
Okay.
kind of.
Well, go back to this one, volume change of gases. Graph the change in concentration of the volume is increased. There's, however, one thing wrong with this reaction. What's wrong with this reaction? Pardon?
It's not balanced.
It's not balanced. So what do you have to do this reaction before you do anything? Balance it. Giving out quizzes and tests sometimes, the students are like, but it wasn't balanced. I'm like, yeah, you're supposed to do that. Sometimes it doesn't tell you. Always check. Balance it. Graph it. I will come back and check. I just realized I haven't picked up your quiz. I need to go get it.
One, two, and then
I don't understand how the
always goes to the lesser side.
Yeah.
Always goes to the lesser side. So it's gonna be
So hard.
I know, but it makes no sense. Like, why?
Because it's like as the like space, like is it space?
As the area,
As
the volume.
Yeah, as the volume like increases, concentration increases. So therefore, it's like you know this like stupid as the volume shows.
Yeah, yeah, yeah.
It's like since there's less of this, it always translates like E to it.
Yeah.
And once less
Oh.
of these, so that we can make more of this and we don't have the smaller areas.
Yeah.
So that's why it's
But how does
how does that work?
and also like how does that even make sense? Because let's just say there's like 2 of these that are let's just say there's 4 of them, okay? And then you said what happens to them? They get removed?
No, like they still because there's like
It's
gonna be
still
some
should
sort of problems.
Yeah, so that kind of.
And there's gonna be like
But
let's say
for
there's a
molecules
lot
too, right?
of stars.
Like three.
But they would be at equilibrium, wouldn't they?
Yeah, let's say they're odd.
So that's just like one.
Wait, but then that's about
And why?
four. That's a balance of races, like, for
Today's Tuesday. We got till 9:35.
You got 3.
No, like
Oh, yeah.
Keep an eye on things.
That, I would go for the molecules, not the like balancing.
Okay. We usually go.
so shift to the products which means
No, I don't think we did.
Mr. Newfield?
I did not think that was.
You are decreasing the volume.
Mr. Newfield? I need your help.
There we go.
I need your help. For like this slide, if you
Yeah.
say that you make the analogy.
This is saying that it's a 3-to-2 ratio of
Okay, yeah.
at equilibrium.
Yep.
Food cutie. Do you
So
see
that's
how
just the
this-
balancing, the
these
3 to
little
2.
things?
Aren't you saying something about how like, is, as the volume
Do you count,
increases,
like,
then the
So that's like
concentration?
2. Like
Increase,
molecules.
yep.
It's just
Therefore,
these.
like, we're gonna move out
So
3 of
this
the
one's
scholars,
So
and then we're gonna bring in 2 of the
Sure.
2.
Yeah, yeah. Because it will shift to the side with the fewer
I know that
molecules
part,
because
but
you're
like, how do you
decreasing the
like
volume,
each?
made the pressure go up, there's more particles, they got crowded. By shifting to the
Like,
side
how
of
do you
2,
like
they're
know
less
how
crowded.
much to-
Yeah.
Got rid of
This
some.
one
Like,
is
what would be
gonna
the factor then?
Now, on the question we're doing now, we've actually increased the
like
size.
if this is a hole,
Which way is it going to go down?
that could be
Then
like
it's gonna be more of
this
these.
one could be like 1.
Right, yeah, it'll shift towards the stars because now it can increase the number of molecules that way. You can take 2 smaller cases
I
and
guess
increase
this
stars.
one could be 1.
Yeah, graph that.
So with volume increase means also pressure increase.
That's a wonderful start.
Volume increase means.
That's good.
I mean pressure decrease.
That's good.
Because pressure increases the volume.
So Mr. Newfield,
Okay.
It's like,
Oh,
it's
increase, good.
so it uses
How much is it?
Yeah.
so you know how to return lots or?
After you return it.
After you return?
Increase the volume.
Like this one is like,
Of all.
I don't know.
Terrible.
Like, is there any chance you don't put it in there?
H2.
But it gets taken off the next step.
But then isn't from 1 belongs to 2?
No, no, that's usually like the 25th or 27th or something.
Oh, and are we gonna
We
do
might
that?
have to test before. I don't know for sure.
For the last one, where the ratio of pressure.
Ah, yes, what is the ratio? Did you balance it?
Yeah.
These 2 definitely.
Then you should know the ratio. I don't see it though.
Yeah.
Oh, yeah, yeah.
No, same way, cause it's backwards.
Yeah.
Is this right?
NH2 decreases.
The only thing I think you're missing
You should,
is the spike.
No, they all decrease.
Oh, they all spike.
They would all spike. They would all spike. In which direction would they all spike?
Upward.
Look, if the volume
Down.
is increased,
Why?
Why down?
Concentration because the volume increases the concentration.
of
Yeah.
all.
Like this must be good
Which means that they all.
Yeah, you have them all spiking down.
I don't know that it improves like that, no.
Because I actually don't know.
Question? Senator?
He asked me how I knew why like NH3 like goes down and then goes back up,
Did you do
and then
this,
why
Keith?
H2 and N2 just.
Okay, let's walk through that. First of all, let's balance it. Andrew, what would this be balanced?
Um, 1 N2, 3 H2, N2 NH1.
Right. So what? How many particles are on this side?
3 or 4.
4, and this side is
2.
2. So we're going to see a big shift in direction.
Yeah.
If we increase the volume, what's going to happen to the concentration of every species?
Decrease.
Decrease.
So that's the spike down. So that's why they go down first.
Right.
Okay. So once they go down, which way will allow it to go up overall? Like which side will give it the most particles? Yeah. So it's going to shift that way.
What? I thought it went through. Yeah, it went to the left. The one with the left.
Well, that's because this time it's increasing.
This time it's increasing. Because if we increase the volume, what happened to the concentration? Went down. So we want to increase the concentration overall. We can increase this concentration by 4 by shifting that way and only take away 2. So a net increase of 2.
Wait, but how do we know this in the future?
That's the
You just count the number of particles. So Le Chatelier's principle, whatever you do, nature tries to undo. So if you are increasing the concentration of a gas, increasing the pressure, then it's going to want to reduce that pressure. To reduce that pressure, it has to take away molecules. If you decrease the pressure of a gas, it's now in a partial vacuum, it has to try and increase that pressure. And it does, though, by adding more molecules.
Wait, so is it then the opposite if, yeah,
Yeah, so the other one, the other example, we increase the concentration. For this one, we're decreasing the concentration.
Like for this one, isn't it that if volume increases, then it favors a side with more molecules?
So if volume is increased,
Then it favors a side with more.
yeah, it favors the side with the most
And
molecules.
if it's decreased, then it favors a side with less.
Yeah, literally, yes. Increased volume, that's an increase in pressure and an increase in concentration. I'm writing a lot of symbols, so you could, if you should ask me if you don't know what they mean. So increased volume is also an increase in, I wrote that wrong, what mistake did I make?
Decreases.
Yeah. I got carried away with the sound of my own voice. Increasing of volume is a decrease in pressure, which is also a decrease in the concentration. And then it will shift to side of most molecules.
So to the side that has more entropy.
No, stop saying entropy. This has nothing to do with entropy.
Oh.
You're counting molecules, which is why your brain's going, we did that in entropy, and it wants to make that connection. It doesn't have anything to do with entropy. This has to do with concentration and pressure.
And then how do you know for the graph that NH3 is gonna spike up and then slightly
Whoa, what happened? Which way did they all spike?
down?
Down. Because we decreased all of their concentrations.
Yeah,
Now what will happen to the amount of NH3?
NH3
It's shifting now, it's going to decrease in a 2 to 3 to 1 ratio. So NH3 should go down,
Cause I literally don't know, I didn't understand.
You understand?
like that. And then, if this went down by 2, by how much should NH2 go up compared to NH3?
You said
Wait, could you repeat that?
goes
Repeat that.
down.
This is, what is happening to this concentration after the spike? Decreasing. What is happening to these two concentrations? Both are increasing in what ratio? 3 to 1. And this one should be double, whatever N2 is.
So we'll just draw them less.
Yeah.
Less.
So H2 should go up
A little bit.
a fair amount. Because it's 3 to that one. I think maybe I drew the other one too big. But who cares? There we go. And then the other one should go up
Okay, now
only a wee little amount.
So H2 is gonna go like back.
Almost back to where it was.
And does it spike down like 3 times the amount? Like, what's the ratio?
Of the spike,
Yeah.
the volume changes the same for all of them. So the spike is the same for all of them.
Then how about like the amount it like?
The amount it changes is due to stoichiometry, so it's in the ratio because 1 particle of this reacts with 3 particles of that. So 4 go away to make 2 of that. So all the reactions happen in the ratio. So any changes are by the ratio. Notice their starting points aren't in the ratio. The concentration, the total concentration that they're at could be anything. But the amount they change will always be in the ratio. And once we do ice tables, you'll see that.
And then N2 doesn't go up as much as H2.
Right.
Because
Because it's the one we only need 1 of.
right.
Yeah.
It's not as big as this. So the reaction shifts towards the reactants.
Yep. The reaction shifts towards the reactants. What do we got coming up? Ooh. Any more here? Nope, I don't think I forgot any bits. Last one of what happens. I want you to consider a catalyst. We're not going to write anything just yet. If I had a catalyst to a system, what does a catalyst do to the rate?
Or speeds up the reaction.
Speeds up the reaction. How does it speed up the reaction?
Decreasing
Activation.
Decreasing activation. So what type of reaction is this?
Exothermic.
Exothermic. So we have this reaction here, And it becomes this. Which rate will it speed up, the forward or the reverse? Both. So if we have a reaction and we speed up the forward rate and we speed up the reverse rate, which way is it going to shift? To the products or the reactants?
Hey, can you repeat that?
Well,
Isn't that still dependent?
Pardon?
well, it won't change.
It won't change. A catalyst is absolutely nothing to an equilibrium. So if I measured time, rate, and then once again I say, oh, that's forward, that's reversed, purple being the same one, we go here, and at this point right there, T1, add catalyst. And at the catalyst time, what happens to both rates? They both go up. And if they're both still equal, then what do they do?
Go back to
It just goes back and it stays the same. What would happen to the concentration in that case? Which way would it shift if the rates are faster?
what did I just say?
It would just stay the same. You would see here at T1, where we added the catalyst, you would see the rate of A go The catalyst has absolutely no effect on an equilibrium. If it's not at equilibrium, it'll reach equilibrium faster. So you are increasing rates. But if it's already at equilibrium, it's not going to shift any side. You've advantaged both sides. With a lower activation energy, both of them had an equal opportunity. Remember that one where I had you walk around in a circle to represent dynamic equilibrium, the tables when you just walked around? Took you all aside, I fed you meth, cocaine, I don't know, ADHD drugs, like everything I could think of. You're like, ah! And then they let you go and you're just running around the room. The number of people on both sides would still be the same. I didn't affect the equilibrium. Maybe the volume level in here, and they got really excited. But the equilibrium was unchanged. There's the same number of people on both sides. Going faster didn't change the equilibrium. You have to change it on a side. So catalyst does what to the activation energy?
Doesn't do anything. Oh, after the, yeah,
Reduces.
Reduces, sure. Reduces is a good word. Reduces activation energy, the forward and reverse reaction both. You don't have to make it 2 words.
Reduce, decrease.
The reaction rates, the forward and reverse reaction rate both decrease.
For the forward and reverse reaction.
Yeah.
it increases.
Rates.
Decrease rate or increase rate.
Increase rate would work. By an equal. What were you going to say? Katie?
Significant amount.
Therefore, a system at equilibrium, when you add a catalyst, stays at equilibrium. If a catalyst is added. If not at equilibrium, it would reach equilibrium more efficiently. It's not one I've used before. Efficiently, faster I heard, quicker I heard.
Wait, why is that?
If it's not at equilibrium, the rates are faster. So it will just reach equilibrium really quickly. So our curves wouldn't be as slow, they'd be more sharp.
How does it reach equilibrium?
If we go back, I think I have a rate graph here. So this time from here to there is how quickly it takes to reach equilibrium. If you added a catalyst, then this curve would be towards the equilibrium more quickly because that would just the rate's faster, so they wouldn't take as long to adjust. Does that make sense?
But it was at equilibrium.
It wasn't equilibrium at the beginning here because the rates were different. Forward rate was faster than the reverse rate.
Okay.
And there was equilibrium once they both became the same. They would just both become the same more quickly. over there. Catalyst doesn't do anything. And now we're going to talk about the most famous, I shouldn't say most famous. The most valuable reaction worldwide, discovered by a German chemist. This is known as the Haber process. Andrew, do you still have questions on the last one?
No, kind of, not really. I'm asking for like something related to this.
Do you go back? You quickly do it.
No, it's like kind of related to you. PLD.
Oh, well, we need to move on to this one.
No, it's like I'm getting the fundamentals down to get
Okay.
these points.
But I don't want you to miss this while you're doing that.
Can we get some time to like study for the quiz, please?
Yeah, that was last night.
Oh, really?
Yeah.
And today.
And today before class.
In class.
Not in. No.
What time
We
are
must march on.
starting?
Pardon?
What time are we starting?
Near the end. I gave the last class 15 minutes.
No,
It's a 10-minute quiz. It's 10 questions.
I thought you said
Therefore, we get
Like
20
7
minutes.
multiple choice and 1 3-mark long answer. It's like done.
what's the long answer?
And I might get, actually I think I gave the class 20 minutes.
Here's my
Okay.
phone.
Samuel,
Wait, we have.
I do want you to keep up. If I can go back, I'm happy to go and re-explain. But I also don't want you to be missing things as I go ahead. The Haber process is the most valuable process in the world because without it, I think it's estimated between 4 and 5 billion people would die. It is the responsibility to make fertilizer. If you can take ammonia and you can make that, that is fertilizer. And as much as we try to grow things without fertilizer and you have organic farming, if everybody in the world decided to go to organic farming, between 4 and 5 billion people would die. They would starve to death because we cannot make enough food without fertilizer. Fertilizer allows us to grow multiple crops in the summer, and we need to be able to do that to feed everybody. This is locked up in our atmosphere. It's an exothermic reaction. So it looks like this, but it's more that it looks like that. The activation energy to unlock NaN2, which if you recall from your grade 10 or 11 Lewis diagrams, triple bonded, very strong. To get it to reverse, really, really, really difficult. And so we have a high activation energy to overcome. And previous to the Haber process, the military might of a country was measured in average hours of sunlight on arable land per year, because that's how much food you could grow. And if you could grow that much food, then that's how many soldiers you could feed, and that determined everything about what you could do as your country. After this, it not only makes fertilizer, what else can you make with nitrates and ammonias?
Ammonium.
Ammonium, yes, yes. Does anybody know what TNT is?
Like a bomb.
Yeah, but what does the T, N, and the T stand for? Trinitro, it's toluene, but the nitro part is the important part. Once you make ammonia, it's very easy to make nitrates. You can make trinitrotoluene, you can make anything. So if you can make fertilizer, you can make explosives. Which is why, as soon as Haber did this, he was immediately branded as a war criminal by the rest of the world. He didn't do it to make fertilizer, he did it to make explosives. He was a decorated soldier from World War I. He was a chemist, he was very interested in this process. And he eventually found a way to do this. Everybody else saw it as, oh, you can just make more explosives now. Before this, to make enough explosives for your country, to make gunpowder, to make anything, wars were fought over bat caves. Because bat caves, bats would use for hundreds and hundreds of years, and they poop down below, and then you go to there and you shovel out all the poop and pee and gather it all up because they're rich in nitrates. And you refine it and separate it and you extract all the nitrates, and that will become your gunpowder and your explosives or your fertilizer. You can make a ton of stuff from shit. But as soon as you do this, You didn't have to. And there was a couple times in World War I in which Germany was cut off from a supply of bat caves, and they had to fight battles just to secure where they were getting explosives from. So Haber went around and said, like, I'm going to figure out a way to do this. And he did it. If this was your problem, how would we adjust this equilibrium, given what we know about it, it is all gases, with respect to pressure, temperature, surface system, means do we have to do anything, worry about surface area, what type of system should this be in, etc. So with pressure, what kind of pressure do we want?
Increase the pressure,
Increase the pressure. Why?
because there's less molecules on the right side.
Less molecules. So that way, with that one, we will shift it to the right. I'll pick a different color for the next one. Temperature. Do we want a high pressure or a low pressure?
We want a high.
Sorry, not pressure. High temperature or low temperature?
Probably high one.
Why the highest one?
Because it will help with the reaction rate.
It will help with the reaction. If we have a high temperature, rate will be fastest. Which way will it shift at a high temperature?
To the other side.
Which side? Reactants or products?
So we should, reactants. So
Reactants.
lower the temperature.
If we increase the temperature, it's going to shift that way. But what will happen to the rate?
Increase. Quicker.
The rate will increase, and it's shifting the wrong way. So we've got a nice fast rate, but now we're making the production of nitrogen and hydrogen gas easier, which is not what we want. If we lower the temperature, which way will it shift?
To the products.
Product. So if we lower the temperature, it will go that way. But our rate will be really slow, and we're not going to make very much very quickly. So we're going to have to do a little experimentation here, have sort of a in-between temperature, something where we can get just fast enough rate, but it's shifting over to the right. Do we need to worry about the surface area?
No, because it's gas.
It's all gases, so we don't need to worry about that. What type of system should this be?
Closed.
Why?
Because it must be closed.
To get an equilibrium going, it must be closed, but what do we want to make? Which way do we want this equilibrium to go?
The reaction.
To the reactants. Anybody use ammonia as cleaning compounds?
I don't think so.
You know what ammonia smells like, right? Yeah, you've smelled that before. I had it in class. It's in a lot of cleaning compounds. It can be a liquid. If we can shift it to the right, if we can peel this ammonia off, so if we can reduce this concentration, which way will it shift?
To the reactants.
Pardon?
Wait, reduce one.
If I reduce the amount of ammonia, so in some way I could convince this to become a liquid and like siphon it off, which way will it shift?
The product.
To the products.
To the products. So actually, we don't want a closed system. We want to open it up. We want to take away some of the ammonia. If we can take away some of the ammonia, it will shift to the right. So for this one we didn't do. So we got high pressure. We got take away the ammonia, medium temperature. The other way we can shift the equilibrium, add lots of reactants. Make sure you're constantly injecting lots of N2 and H2. And if you can find a catalyst for that system, just to make the rate go faster, that would help with our temperature problem. Because then we could go to a lower temperature, but have a catalyst to increase the rate regardless. Now where are we at for? 9:34, 9:07.
Wait, we're still on that page.
15. Are you guys okay?
Yeah.
The Haber process was something that we chemists have been trying to do for a very long time. Everybody knew that if you could make ammonia, number one, your armies would be well armed because you could have lots of explosives, you have lots of projectiles, you have lots of ways of blowing things up, but also you can feed your people. You can have a lot of fertilizer. It is a double-edged equilibrium because as much as it can be used to feed the entire world, it can also be used to arm the entire world. And it is such an important reaction, and the story is so wild, I'm actually going to tell you a little bit about it, especially given that Remembrance Day is coming up. Because, and just as a fair warning, this is not in any way a nice story. Pretty much everybody in it dies in some terrible way, or is tragically, and in the end, 5 billion people get to stay alive and are alive right now. You are likely alive right now because the amount of insecurity in the world, food insecurity, the ability to grow your own food and feed other people would not have happened without this reaction. Countries wouldn't have the prosperity they have today if it wasn't for Haber. It's also, I should mention, it's called the Haber, some people call it the Haber-Bosch process, because another chemist named Bosch also had some involvement, or the Haber process. Everybody has that. Shifting gears. 40%, as it says, of all humans likely owe their life to Fritz Haber. Again, I can go back if you're working on a particular question.
No, we're good.
Okay. Fritz Haber is also the person who invented gas warfare. He had his first success with the Haber process. He invented Zyklon A, and his wife was Claire Immerwahr. I'll talk about her on the next slide as well. She was going through life, fairly brilliant chemist. She was the first female chemist to be awarded a PhD in Germany at the time. And then she said, I need to do something in my life at least once to fully experience life. So I know what the next thing I'll do is I'll get married. That was apparently not a good idea. Fritz was a fairly controlling husband. They did work together because once she was married, she wasn't allowed to work, obviously, in a lab. You can't work while you're married and female. My mother was fired from the bank the day she told them that she was getting married. Because if you're female, you cannot work. You have to go home and take care of your husband. Attitudes were similar then. And so she was still really interested in chemistry, so she would work with her husband. And what followed is probably a result of the fact that she may have felt responsible, because a lot of his early work may actually have been a lot of Claire's early work. We're not entirely sure because we don't have the notes from that. But it seems her involvement and her objections really stemmed from a sense of personal responsibility. He invented, as I said, the first use of chlorine gas. So in World War I, the Canadians were encountering the first use of chlorine gas on the battlefield. In the Second Battle of Ypres, the Canadians actually did much better than the French and Algerians because they smelled the gas and immediately knew what it was because they grew up drinking chlorinated water. Because if you live in a remote area in Canada, other than these civilized places like the UK, you would chlorinate your water to kill all the bugs. So the Canadians recognized this as chlorine, they covered up faster, and they survived better. Didn't help them because the next day they had to make up for the losses of the French and the Algerians, and then they were surrounded on 3 sides by chemical warfare, and a lot of them died. After that, the Canadians developed a particular reputation when it came to Germans. They would throw food over. You may have you heard about the Christmas peace times in World War? Canadians didn't do that. Germans would come up, they'd offer cigars and foods, and the Canadians opened fire. There is no recorded instance in which the Canadians ever participated. We would throw food over to the German lines and get them used to coming over for an extra breakfast. And then on the 3rd day or the 4th day, whenever it was comfortable, we'd throw grenades. And I say we, but I wasn't Canadian then. My relatives were over in Russia fleeing the Russian Revolution, most likely. So they did nighttime raids. Canadians got particularly good at it. Most other countries got to the point where like, this is a little much even for us in World War II. Like we shouldn't be sneaking into other people's trenches and killing them in their sleep. And the Canadians said, more of that, please. On the night before, what is our famous battle? Vimy, I think it was. The night before Vimy, or the nights before, was estimated up to 900 Canadians were sneaking through enemy lines and killing people in their sleep night after night after night, up to a kilometer away. So you'd be a kilometer away from the front, you think you're perfectly safe, and then you wake up to some person standing over you with a bayonet, and that would be the last thing that you would see. And now we drink bad coffee, play hockey, and large parts of war crimes were written because of what Canadians did, apparently, in World War I. And it doesn't directly ever say that it was because we experienced chemical warfare first as well. But it seemed, in terms of correlation versus causation, to start right after that. So Fritz Haber might also be a little bit responsible for that. He was really eager to do chemical warfare as well. Other German generals were like, this is a bit much even for us. And he's like, you don't understand. I'm a chemist. This is really, really cool. Let's do it. As the chlorine gas went across the battlefield, it was like a cartoon with like birds flying into mortar. They'd hit the gas and drop down dead. Plants would just sort of shrivel up, turn brown, and die. It was a really thick, oily yellow gas. And then it would hit the soldiers. It would absorb through the skin into the lungs. And you would drown because it would come into your lungs would become inflamed, and you'd put out a lot of water. He also invented Zyklon A. Zyklon B is what was used in the gas chambers of World War II. He's also Jewish, so in World War I, he's a decorated war hero. Afterwards, for his use of chemical weapons, he invented the entire genre. And as much as some German generals didn't really like that, they couldn't argue with the fact that it got results. And so he was decorated, and he was given an entire chemical institute in order to continue researching. One of the things he researched was Zyklon A that was eventually taken off the shelves and made into Zyklon B. Zyklon B is the same molecule. They just took off the piece that he had added that made it smell, so it had a warning smell. Zyklon B didn't have the warning smell. They just took that off and used that in the gas chambers. It likely killed his entire family. Except for him. He escaped, died of a heart attack in exile. It may be that he committed suicide, but the reports sort of suggest that. But also people didn't like to say that at the time, so we can't really tell if people are just avoiding that. Not a nice story. Claire, also not a nice story, but I think it's important to recognize other people who are involved in the work. She may have been involved in the Haber process as well. She was certainly a really good chemist. To be a female chemist, to be awarded your first PhD, you would have had to have really good work and be really accomplished to do that. Also Jewish, first woman to be awarded a PhD. She was a pacifist in the war and a feminist. She didn't get any recognition, naturally, for her contribution to her husband's work, so we just have a guesstimate. She felt responsible, however, it looks like, from all of her writings, for chemical warfare as well, in particular. And we think Fritz's early work on both the Haber process and chemical warfare also had Clara's hand in it. So we recognize this entire story. We've got two people here. There's about 5 people today that owe their life to this entire process. It was done mostly just to try and blow people up. But afterwards, we have this very useful reaction in which we can make ammonia, we can fertilize the entire world. If you order fertilizer right now, there's certain types. If you order it to Vancouver Island, you'll get a call from CSIS saying, why are you ordering this? Because fertilizer and explosives are actually mostly the same thing. When I was about 14 or 15, I tried to order a fairly large, if you order fertilizer for a farm, it comes in bags about this high, about that wide. And it was a type of fertilizer really high in nitrates. Essentially, you just stick an igniter into it and you've made a bomb, like it's its own explosive. And then I said, Dad, let's order this one. And then he got a call from CSIS asking why he wanted it, because the only reason you need that is if you were growing, pineapple and tropical plants in really warm Greece and houses that need a huge amount of nitrates. And my dad comes to me like, why'd you want this? I'm like, I wanted to make some bombs. I didn't know CSIS would actually call you, sorry. And then he explained that I just have a dumb kid. No, I don't actually want it, never mind. Miss Stewart has to go through criminal records checks every once in a while, because the stuff we ordered from the school, you could easily make a variety of explosives out of it. So they'll check every once in a while. Are you a real school? Are you secretly siphoning this away? One of the most unrealistic things of Breaking Bad is not the chemistry. The chemistry is fairly realistic. It's the fact you can walk into a chemistry lab, a high school chemistry lab, and just have bottles of the chemicals that he wanted, like hydrofluoric acid. No high school would have that much. But you could dissolve the entire school with that amount. It would be absolutely amazing. Okay, 9:18. Let's go for your quiz. Put everything away. And I had your data table. It's brand new. Mostly new. The other class also used it. So if it has too much writing in it, let me know. It has a nicer picture. Please spread out. There's lots of free tables if you need to move over. Spread out, spread out, spread out. There's lots of tables over here. Over there. Let me not get one. Different illustration. At the last minute I requested art, and nobody gave me art. It was probably 2 at the last minute. If you give me any actual art, I will put it on the data booklet. I generated that with AI.
Could this drop our midterm
Yeah.
marks?
Pardon?
Could this drop our midterm marks?
I don't know. I'm not going to answer that now. You're going to write a quiz. Stop panicking about your marks. Panic about your marks after the quiz.
You don't have to write this quiz, please.
Pardon?
You said you don't have to write this quiz last time.
You don't have to what?
Write the quiz last time you said.
No, I've never said that.
Really?
Yeah, you're here. You can do a quiz.
I heard you saying that you told us
On
that.
the website you said it was, or on the classroom you said it's optional.
Yeah.
With this quiz?
Yeah.
This is lies. Show me where it says that. Also, how could it possibly harm you if eventually it's going to go away?
You're just gonna look bad for midterm marks.
Well, you probably write a test before then. If you don't, and you write it shortly afterwards, you can update your marks.
What?
There you go. Sonia, I'm going to call and have you come to me. Because that might be
What are
faster.
the
Andrew,
questions?
Nathan,
This is a dumb book. Yeah, but where are the questions at?
Katie,
Oh.
Nicholas,
Don't trip.
is not here. Johan,
Okay.
Taz. Oh, I think you're remembering a previous quiz that I assigned more at the last minute.
I might be, honestly.
Gleb? Now that I think about it.
Is this K-Back?
Yeah, it was this.
I thought that applied to all of these.
No. Actually,
You did say that,
Oh, yeah.
K-Back.
Like in class, you're like, you can
Because
not
I-
take
that's
the
'cause I-
quiz,
Security is the change in,
but it's.
me, I was not in this class yet.
like,
what does this KBAT mean?
It's
math.
Oh, your quiz is gonna come out, it's gonna say KBAC C on it, just cross it out, write D, max. And does everybody have one? You have an answer sheet?
Yeah.
Okay.
This is just 10 questions.
written incorrectly on the quiz. I just forgot to change it. It is actually KVAC D at the top. And please color in your version number on the bottom of your response sheet.